Okay, hi and good day everyone. We proceed to our lecture. Okay, yesterday we have discussed in great detail about the function of or the importance of the clock in our sequential design, and we also have discussed detail what we call VLSI flow chart. Okay, VLSI design flow. Okay, so this is basically the general flow of the VLSI design. Okay, beginning from system specification, okay, until fabrication and testing of the chip. Okay, so basically we also have discussed about there are three types of verification that normally done by the designer. Okay, normally performed by them. Okay, functional verification, where we verify the functionality or the behavior of the design. Okay, once you finish write the design in Verilog or HDL, okay, they will do a functional verification. Okay, and then after synthesis, so this is actually the synthesis part. Okay, after the synthesis process, we also do the verification to make sure that the synthesized circuits function as expected. Okay. Then we also have and the final verification, where we call as layout verification. So layout verification, the main target is similar, is to make sure that our design is working as expected when we successfully implement the design in the physical form. Okay, so when we talk about physical design, okay, so floor planning is one of the step. Okay, it's actually the first step in the physical design, right? So we have also discussed what is actually the floor planning, and then here is actually the definition, okay, which it is estimates the area of major unit in the chip and define the placement. So that's actually the main or important keywords lah. Okay, estimate the area of major unit in the chip and also define relative placement. Okay, the floor plan is essential to determine whether a proposed design will fit in the targeted area of the chip. Okay, so you have the die, and then we plan. Okay, what is actually the maximum possible core area? Okay, maximum possible core area. Okay, we have an example in our textbooks. Okay, from that example, given 1.5 by 1.5 die. Okay, and then given a process technology of 0.6. Okay, and then from the 0.6, we can get the equivalent lambda. Okay, so we have also discussed about what is actually lambda and how to get it. So based on assumption, lambda is actually half of the channel length, so we assume it 0.3 micrometer. So 0.3 micrometer, you get it, and then you convert the 1.5 millimeter, okay, to equivalent micrometer, so that for easy cancellation. So 1,500 divided by 0.3, and then you get 5,000 lambda. So this is actually the size when we convert from millimeter to lambda. Okay, so that's why you can see here the size or the dimension of the die, actually 5,000 by 5,000 lambda. Okay, to get the maximum possible core area. Core area means that the area that we can utilize the control and also the data path in it. Okay, so other standard is actually allocated for power. Okay, power is actually for VDD and also ground lah. Okay, and then also for the I/O, which is very important lah. So if a chip without I/O, then nothing lah. So you need to have you have I/Os, so that the chip can interface or interact with the outside world. Okay, so we have here, maybe I use different color to make it more interesting. So we have 10 I/O on the left side, okay, the other 10 on the right, and the other 10 on the top, and the other 10 at the bottom. So all together for this I/O. Okay, so at the corner of each, okay, normally they allocated a power. That's actually the basic, right? So that's actually a process of floor planning. How do people do, or designer do the floor planning? And then to get the what we call the maximum possible core area, so we use this what we call relationship lah. It's given as each pad, IO pad tu dia punya size dia 750 by 350. So 750, I believe this is actually 750 if you notice from the textbook. So this is 750 lambda, okay, and this is also 750 lambda. So 750 by and 750 total, and then you divide it by you subtract this one, subtract by these two, and then you get 3000 by 3000, 3500 by 3500. So same, okay. So 3500 by 3500, and then the area in terms of area is actually about 12.25 lah, mega lambda square. Okay. Okay. Here we have question. It asks you why it should be in rectangular. So normally the size, the rectangular is actually the easiest dimension for us to do the estimation. And this is actually the actual chip. Okay, this you will see in Synopsys IC, IC compact IC in Lab 2. Okay, here you can see clearly the power. Okay, and then the rest IO and also the core. Okay, here is the core. Okay. All right. And in terms of controller, so here is actually the detail of the controller. You can see in the textbook lah. So the controller, which is this one, this part. So the dimension of the controller is 2550 by 380, and also the data path. This is actually the dimension. Okay, and contribute to the area of 3.4 mega lambda, and this is 4.8 mega lambda square. Okay, so most of the area in the controller layout are dominated by the routing channel. You can see clearly here lah. Okay, a lot of areas here actually routing, wiring, do the interconnection between the subunits lah. Okay, that's actually the nature lah, what happened in the IC design layout. Okay, you see a lot of wires there. Okay, the logic you can see here, these are the logic compared to wire is more, routing is more. Here is actually the layout for the data path. Okay, just now controller, and then here is data path. So for the data path, this is actually the extension of this, okay, of this part, or maybe somewhere here lah. Okay, somewhere here. Okay, so the data path, okay, we have from bit slice 0 until bit slice 7. Okay, so altogether 8 lah. So 8 bit slices plus one additional, they call it as for zipper, and we have another 3. 1, if you can see here, 1, 2, and then 3. Okay, 8 plus 1, 9, 9 plus 3, 12 lah, all together 12. Okay, so on the left and on the right, just the power. Okay, this is the power and also ground. Power and ground. So normally power we put both side lah. Okay, okay, to make sure that the supply arrive to the logic resources what we call evenly lah. Okay, we get it. Okay, and then in terms of the size of the wire, okay, it's also bigger than the other area, the other element. Okay, you will see this later. Okay, and this is more actually detailed explanation. Okay, you can get it from the textbook lah. It's explained in very detailed, actually very detailed. Okay, for example, inside the data path here, okay, inside the data path here, this is actually the data path. We have what we call as, they call as slice plan. Okay, so slice plan will make sure, or will determine the what we call the size of the data path. Okay, how do we determine the size? You just look at this. Okay, see this number. So this actually depends on the number of the bit. Okay, when you sum up all of this, you will get the total number of the what we call, I think inside the textbook is mentioned to you, the floor plan. Maybe I can control find. So, oh, we cannot move. Try floor plan. Floor plan tinggal lah saja tadi. Floor plan. Okay, here. Okay, so under floor plan, if you go here and then under the data path, they have an explanation how do they hire here. Okay, so maybe I can highlight here. So total 319. Okay, the total. So when we're adding up the width of each element, which is this one, okay, this. Oh, we use this, and then you will get 319 track, or the size of 255, 2 lambda. Okay, and that's why you can see inside the lecture to the size 255 or 250, if I'm not mistaken. Yeah, 250. Okay, for the data part. Okay. All right, so the slice plan actually shows you the interaction, actually how the connection. For example, how the PC here, PC is connected to the flock here, PC flock here. PC flock is connected to the address multiplexer. Okay, until here. Okay, so this is actually the interconnection, and then how it's connected to source A. Okay, from PC is connected to source A. Okay, and then goes to the other area. Okay, this is actually the diagram or slice plan they call. And here it's actually the area estimation. Area estimation. How do people or designers estimate the area of the die? Okay, based on the typical layout densities. They call it as typical layout density. So typical means that it's based on their experience. Okay. So random logic with 2 metal layers, normally the size actually around 1000 to 1500 lambda square per transistor. Okay, per transistor or one transistor. Okay, for the data pass, this is actually the estimation. For SRAM, this you can see here, just to implement one bit memory, it requires 1000 lambda square. Okay, compared to the DRAM. One question I like to ask you, why SRAM requires more area? This is area, more area compared to the DRAM. Any answer? Ada jawapan? If you have the answer, then we will stop the lecture. We continue to the briefing, and then you will finish early. That's my promise. We will not go to the sequential circuits. Any question? Any question? Any answer? I repeat the question. Why SRAM requires more area? So you can see here, 1000 divided by 100, you get 10, factor of 10 in terms of area reduction. Okay, if you use DRAM. Okay, in terms of area per bit. So why?
Doktor.
Yeah.
Sebab dia constantly refresh dan dia faster dengan DRAM. So dia ada banyak part dengan wiring. Sebab tu dia ambil banyak space on chip.
Okay. Okay, good. Nearly there. So in terms of number of transistor, SRAM and DRAM.
Dia perlukan lebih transistor per bit compared to DRAM.
Okay, correct. So Pang Kai Z also try to answer more transistor. Yeah. So in terms of number of transistor, SRAM utilize or uses more transistors compared to DRAM. Okay, just to represent one bit. So that's why it requires more area. Okay, if you can see, if you Google, you can see lah. Okay, you can if you recall back your lecture on digital. Okay, digital design, SRAM requires more area compared to DRAM, because SRAM, if I'm not mistaken, it requires 6 transistors to implement one bit, and DRAM only 2 transistors. Okay, 2 transistors. Okay, good. Thank you. Okay, so typically routed standard cell layout density measured. So normally measured in kilogates, kg gates, kilogate per millimeter square. So for your lab, you will see it measured in number of gates lah. Okay. All right. So a gate equal to 3 input static CMOS NAND or NOR gate with 6 transistors. So normally we use either NOR or NAND gate. Okay, to represent a logic lah. For example, AND gate, for example, normally they will convert it to NOR, to NAND and so on. Right? So that's how the design happen lah. Okay, so as I promised, I will stop here. Okay, we proceed to the what we call the briefing on the lab. Okay, so we go back to wait. Okay, so we go to the lab. All right. So for lab, or maybe I just go to lab 0 first lah. Lab 0. Okay. Lab 0. Okay, I think part B will tell you detail. Okay. Okay, just wait for a while for the system to load. Okay, so lab 0, okay, as I mentioned to you all, you can use it straight away for implementing your assigned logic lah, or your assigned task. Okay, either subtractor or divider or whatever you want to apply, counter, ALU and so on. Okay, simple lah, okay, simple one. Okay, I also jot down important information lah, because this is due to maybe some of the students who have tried lab 0, they come up with problem, and then I actually provide the solution. For example, if the window are idle, you click on window and nothing happen, then you hit the window button on your keyboard and then you proceed to click any of the item on the screen, and then it should be okay. Okay, as this happens sometime, not all the time lah. Okay, sometimes. Okay, when that happen, then you use that way. We also have the recorded video lah, telling you how to demonstrated to you how to solve that problem under the title of window button, okay, and log off. That's actually the title. You have feel free to explore it. Okay, and then to complete the report, actually I'm expect you all to understand the flow. That's actually the basic and relate to the ASIC design flow. For example, here we have the flow like you write the, I think under this, we go to this first. Okay, this is actually the flow. You can relate this flow to the task that is being given to you. Okay, for example, you create the design. Okay, design entry using Verilog HDL code, and then what you do, actually you create a test bench, and then what is actually the purpose of test bench, and actually what is actually the content in the test bench in brief. Okay, you can put the coding as an appendix lah. Okay, and then you explain what happened. Okay, we do a functional verification, as I mentioned. So this is the first verification in IC design flow. We do the verification whether the multiplier work as expected or not through the what we call waveform. And then after that, you finish lab 0 part A, and then you do part B. So in one report this is we call as lab number 1 in your task. Okay, and then logic synthesis. What is actually logic synthesis? You should be able to define it, explain it using your own words in your report. Okay, and then not too detailed very brief, but we all can understand when we read the report. Okay, and then you do what we call using a design vision. What is actually design vision? The purpose of design vision is actually to synthesize your written code to equivalent logic gates. Okay, so normally we use a standard cell. Okay, and then that standard cell also will be available at the end of the lab. You will be able to see it in the form of gate. Okay, so as you go along, you will also see the explanation to come together. Lots of explanation. All right. So the explanation will tell you, will give you information on how to understand the flow as well. Okay, here is actually the library that you set. Okay, if you feel you not understand enough, this is not detailed enough, you can Google, get it from the synopsis reference manual under the synopsis website. Okay, link library, why we do a link and so on. Okay, try to understand the flow here, and also explanation also here. Okay, right, so the comment here is actually I give for you all to understand lah. Okay, same as unique Q file. Unique Q file is very important. When you go to this step, some of the student might not able to solve this step because of they forgot to identify it as the name of the designer. When you need to zoom in, and then, for example, in this case, MULT11. So you can see it clearly. Okay, MUT_11. We put in here MUT_11, not multiplier. So that's actually the most what we call typical problem faced by the student. Okay, not multiplier, mul_15. Okay, it depends on your design. Maybe in your design mul_13 and so on. So it's not exactly the same as what you will see in the lab manual. Okay, this as I mentioned to everyone yesterday. So your design has a clock, for example, that multiplier. So skip step A and then proceed to step B to create the clock. Okay, and then this is actually the clock period. 40 is actually the clock period. You can play around with this. You can make it smaller. For example, make it 20. And in terms of the duty cycle, or in terms of the clock, half of the clock period, it's actually, this is 20 lah, half of the 40. If this is 20, this is 10 lah. Okay, and so on. Okay, so what is actually clock latency? When you go into this, you need to explain in your lab report. You did this, for example, set clock latency 0.3. So what is actually clock latency? We have discussed in detail in our lecture, and under the topic of synchronous or sequential system, on topic of the sequential, if I'm not mistaken, under your lecture Okay, sequential circuit, we will also discuss in detail. So I give you time to explore first, okay, to do the lab. So all of this inside your textbook, don't worry. Inside the textbook, it explained to you in very detail, in a great detail. Okay, you go to, for example, here, okay, the delays in the circuit, setup and hold time, okay, and so on, the propagation delay, including the delays that we discussed in our lab. Where's the lab? Tak ingat lah. Okay, clock latency. Okay, clock latency. You can get it from the textbook as well. Just use the Control F, and then that will bring you to the definition, and then you will get it. Okay, so the next step, set input delay. So what is input delay? So we have 4 input in our design. Okay, clock, reset, input 0, input 1. So they actually, each of the input got its own delay. So in this case, we set to 2.0. The unit is normally 9 nanosecond. Okay, that's actually the delay, the wiring delay inside the port. Okay, this is very important. And then there's output delays. Okay, this will actually help you when you have this. You explain in the report, that will contribute to the marks. And you set the load. Okay, actually what is that happen? set the fan out. So you also learn in digital system, okay? And then we set the fan out load of 8, okay? And then you do the optimization. We set it to 0 for area. We can also optimize in terms of speed. Okay, just clear the max area. You can explore it in the lab. Try to play around with this and see the report. Okay. And then it's come to the end of the lab lah. You will follow all of this. And then the other thing that I like to highlight here, this step lah. This step is a bit tricky too. Okay. For example, when you finish the previous step, okay, the mapping and so on, the area estimation and optimization, and then you want to view the what we call the schematic. Okay, normally the schematic sometimes is gone. So to view it again, so normally you go to hierarchy and then click new logical hierarchy view, and then it will pop up again lah. Okay, with the schematic. So here I also what we call not all the important information. So hierarchy, new hierarchy logical view. Okay, and then from there you will see it like schematic. Okay, but at the top level first, like this one. This is actually what we call as top level. Okay, if you intended to see inside, you can double click inside this. Okay, okay, and then see the detail. Okay, so the next step, you wanted to see the critical path. So this is actually another challenging task. Some students, even me, when I make the video, recorded video, I cannot get the white line. Sometimes we need to repeat multiple times until we get it. So in the case of you didn't get it, okay, I also give you the alternative, like this one. Alternatively, if no white line is actually the critical path shown, click on the top level. So you click on this top level, and then of the design, okay, of the design autopon, or you can also click to the name of the multiplier like this one. Click on this, then you go to the step, next step, select pass from or through or to, and then you proceed saja the next step. Okay, you will see the white line with only the element as I mentioned here lah. This time only component related to the critical path shown. So normally like that lah, not the detail of this. So this is also acceptable. Okay, why that's so important? Because you need to update in your report lah. Okay, and the last and very important step, you need to save your file. You need to save your file as .ddc. Okay, depending on name of your designer, adder, subtractor, or divider, whatever. Okay, underscore syn.ddc. Okay, this file will be used for lab number 2. If your file not okay, your lab number 2 will not okay. So make sure you follow the step. If your file okay, your lab number 2, you will get the result as expected. Okay. And the other thing is very important too. Please copy the log file. Log file normally when you run your, you see here log. Okay, you click on this tab. Okay, and then you Control A, you copy all this, and then you paste on the notepad or WordPad. Okay, you save it. Same like history lah. History file also you can click on this tab and then you copy all. Okay, and then paste in another what we call another notepad file or WordPad file. Okay, you have these two files, and then you can either attach if that file is too long. Oh, it's okay because you not submitting the hard copy. It's okay. You attach these two as an appendix together with the coding, right? Okay, and then in terms of lab attendance, okay, I already put in your team class. Okay, and that's all about this one. Any question before we proceed? No need to answer this. Okay, any question before we proceed? No. If no, we go to lab 1 assignment. Okay. Instruction. So I already assigned you all. So this is actually the instruction. So based on lab 0, okay, apply the assigned topic. So the assigned topic already given to you for each of the group, either n-bit adder, n-bit subtractor, or n-bit divider, or whatever design that you want to design lah. and the number of bit is up to you. Okay, that's your flexibility, and then that's also will actually differentiate between yours and other group. So kalau nampak sama sangat tu, I might be tag as copy lah. But if you can see different, and then that will reduce the tendency of copy lah. That's my assumption lah. Okay, so I also mentioned here, please note that n term represent number of bit. It can be any size lah, depend on you. It varies from group and depending on your design creativity or flexibility. I give flexibility to you. Even the design unit also is up to you. So any group with a unique design may use other than assigned design unit, yeah, except the multiplier lah. Okay, and finally we'll get extra marks. Okay, for group leader, compile each of the section done by group members, and then the group leader only to submit. Okay, the rest no need to submit. If you submit juga, nanti I will, when giving mark to you, I will confuse. So just group leader compile and submit. Okay, alright. So normally the group leader tu the one at the top lah, nama yang dekat atas. Okay. So each of the group member, so this I mentioned each means that everyone is in the group lah, in that particular group. Contoh group of 3, so each of the 3 group member to need to fill in the attendance mark, not isi this one. So this is a link. Okay, back sikit, it'll take some time. Okay, your email, your full name, your program, your group number, so that I can identify you easily, and then your group session, your metric number. These are the 2 files, the log file that I mentioned to you in the txt format, and then the history. And I only request you for log file, not history. Okay, log file only. Okay, and then for IC compiler, it's actually for lab number 2. Okay. No need lah for lab number 1, no need to submit this. So I need that file, every one of you. Okay, and then in terms of the template, just follow this one. The topic you write here the topic of yours lah. Okay, and bit is the name. You can give the number of bit that you have decided within the group lah. Okay, name of group leader, and then the members. I put it 4 because some of the group got 4 members. I think the only 1 group got, the rest only 3. Okay, and then the timing report. Okay, just fill in and then the explanation here. Okay, I just put 1 page lah to make it simple. No need to explain too detail lah. Okay, at least using your own word and then I can explain, then it's okay. This is just a suggestion. If you need additional pages, and then you can tab lah. Okay, but not too much lah. Okay, in terms of appendix, you just incorporate or attach your design code, your test bench code, and then the log report and also the history report. Okay, that's all. Any question? Ada soalan tak? Any question? Kalau tak ada soalan, saya akan beritahu assignment. Saya bagi siap-siap lah. I give you the assignment siap-siap lah. Okay, early lah, so that you can have a plan. So these are the title. Senang saja saya nak bagi. Saya copy paste saja. Any question? Ada soalan tak?
No question, Doctor.
Sorry?
No question.
Oh, no question. Okay. So assignment number 1 and number 2 the same lah. Okay. So maybe assignment number 1, number 2 the same. So topic for group number 1 same as itulah. So I just copy paste lah. So I think that's all. So I need to stop the recording first. Thank you everyone. So if no question, we'll see you next week lah. Okay.
Thank you, Doctor.